There is a story in physics. It's a quiet one, whispered in the hushed halls of research labs, scrawled on chalkboards late at night. It's not about monsters or ghosts in the traditional sense. The ghost in this story is the universe itself. The story is about a single, unimaginably small particle that could, in an instant, change everything. It's a tale of an invisible field that permeates all of reality, a field that might not be as stable as we think. This is the story of the Higgs field and a concept so profound, vacuum decay. This idea doesn't come from science fiction. It emerges directly from the equations we use to describe the fundamental nature of our universe, a possibility embedded within the standard model of particle physics. The same theory that explains the particles that make you me and the stars above also contains this faint, chilling whisper of an ultimate catastrophe. It suggests the fabric of space-time might be temporary, waiting for a single, random event to tear it all down and remake it into something utterly alien. Imagine the universe as a calm, placid lake. You can sail on it, you can swim in it, you can live your life by its shores. It seems permanent, solid, dependable. But what if, deep beneath the surface, the water was in a state it wasn't meant to be in? What if there was another, more natural state it could fall into? The transition wouldn't be gentle. A cataclysmic shift, a flash of change that rewrites the laws of what it means to be a lake. This is the essence of vacuum decay. We are living on the surface, unaware of the tension in the depths. This isn't a prediction, it's a possibility. A what-if that pushes the boundaries of knowledge and forces us to confront the terrifying scale of the cosmos. The particle that could trigger this change isn't a villain, it's a messenger. The universe is not obligated to make sense to us. It simply is. To understand it, we must be brave enough to ask the scariest questions. What if it could all just end? To understand this cosmic ghost story, you have to first understand the stage on which it's set. That stage is the Higgs field. You can't see it. You can't touch it. But it is everywhere. It fills every cubic centimeter of space in the entire universe. The empty void between galaxies, the space between the atoms in your own body. Think of it as a kind of invisible, cosmic molasses that permeates everything. Without this field, the universe as we know it could not exist. Its most famous job, the reason it got its name, is to give mass to fundamental particles. Particles like electrons, quarks get their heft by interacting with this field. Imagine trying to run through a swimming pool. The water resists your movement. It makes you feel heavier, harder to accelerate. The Higgs field does something similar for particles. Some particles, like photons of light, don't interact with it at all. They zip through it as if it isn't there, and so they have no mass and travel at the ultimate cosmic speed limit. Others interact with it strongly, and they become heavy. The Higgs boson, discovered in 2012, is a ripple in this field, proof that the field is real. Now, every field in physics seeks to be in its lowest possible energy state. It wants to relax. Think of a stretched rubber band. It holds potential energy. When you let it go, it snaps back to its relaxed, low-energy state. Scientists believe the Higgs field is currently in a certain energy state, which dictates the laws of physics we observe. The strength of this field determines the masses of all particles. It sets the rules for how atoms form, how stars ignite, how chemistry works. The universe we see is a direct consequence of the Higgs field being exactly as it is. But here's the crucial question. Is the current state of the Higgs field truly the lowest possible energy state? Or is it just resting in a temporary dip, a seemingly stable but ultimately precarious position? This is the difference between a true vacuum and a false vacuum. A true vacuum would be the absolute rock-bottom lowest energy state possible. Let's make this simple. The concept of a false vacuum, a ball on a hilly landscape. Imagine a wide, shallow dip on the side of a large hill. A ball placed in this dip will stay put. Nudge it a little and it rolls back to the bottom. It seems stable. It seems safe. This is our universe. The ball's position, the Higgs field's energy state. For billions of years, the ball sat comfortably here. Everything has been fine. We call this metastable. Now imagine, elsewhere, a much deeper, wider valley. This is the true vacuum, the lowest energy state. To get there, the ball needs a push. It must be knocked over the small hill into the Great Valley. Once it starts rolling down, there's no stopping it. It releases a huge amount of energy as it falls. Then it settles into a new, permanent resting place. The ball will be stable, truly stable, forever. The problem is what happens during that fall. For the Higgs field, that transition is vacuum decay. The push could come from a few places. 1. A random quantum fluctuation, quantum tunneling, like the ball suddenly appearing on the other side of the ridge. It's incredibly unlikely, but not impossible. 2. A very high-energy event. For example, 2 extremely powerful cosmic rays colliding. That could create a tiny region with enough energy. So, a single random event happens somewhere in the vastness of the cosmos. A quantum fluctuation, a freak particle collision, something gives the Higgs field the nudge it needs. In that tiny point in space, the field tumbles into its true vacuum state. A bubble is born. A bubble of new reality. This bubble isn't made of soap and water. It's made of a different kind of space-time, one governed by new laws of physics. Inside this bubble, the Higgs field has a different value. And because of that, everything is different. Once created, this bubble of true vacuum would immediately begin to expand in all directions at nearly the speed of light. Why so fast? Because the true vacuum state is, by definition, more stable and has lower energy. The universe wants to be in this state. The expansion is not an explosion pushing matter outward. It is the fabric of space itself converting from the false state to the true state. The wall of this bubble is a rushing, shimmering frontier between the old universe and the new one. It is the ultimate boundary, moving so fast that nothing can outrun it. The probability of this happening is a subject of intense scientific debate. It all depends on the precise masses of fundamental particles, especially the Higgs boson and the top quark. Our current measurements suggest that our universe might be metastable, but just barely. The estimated lifetime of our vacuum state is fantastically long. Trillions upon trillions of years, far longer than the current age of the universe. So, while the gun might be loaded, the trigger seems to be incredibly hard to pull. Let's paint the picture. What would happen if this bubble of true vacuum were to sweep over the Earth? The word destruction doesn't quite do it justice. It would not be an explosion of fire and light. It would be quieter and far more final. As the bubble wall passed through you, the Higgs field around you would snap into its new low-energy state. The fundamental rules that govern matter would instantly change. The consequences would be immediate and absolute. We wouldn't even have time to register that something was wrong. Inside the bubble, the interaction strength with the new Higgs field would be different. This means particles might suddenly become massless, or gain entirely new, bizarre masses. An electron might no longer be an electron. The quarks that make up protons and neutrons in the nucleus of every atom could fly apart, no longer bound together. Atoms themselves would cease to exist. Molecules would instantly dissolve into a chaotic soup of fundamental particles. Rocks would instantly dissolve into a chaotic soup of fundamental particles. Water would instantly dissolve into a chaotic soup of fundamental particles. Planets would instantly dissolve into a chaotic soup of fundamental particles. Stars would instantly dissolve into a chaotic soup of fundamental particles. People would instantly dissolve into a chaotic soup of fundamental particles. There would be no spectacle, no Hollywood blockbuster moment with cities crumbling and people screaming. From our perspective, it would be instantaneous oblivion. One moment, you are reading this essay. The next, you are not. The Earth would be gone, replaced by a region of space with different properties. The Sun would be gone, replaced by a region of space with different properties. Our entire solar system would be gone, replaced by a region of space with different properties. The thought of an unstoppable bubble of nothingness erasing the cosmos is, to put it mildly, terrifying. It's the ultimate existential threat, a problem you can't solve, outrun, or even see coming. It's natural to feel a sense of dread. But as scientists, our job is to replace dread with data and perspective. The first and most important piece of perspective is this. We do not know for sure if our vacuum is actually false. Our calculations are on the edge. A slight change in the measured mass of a particle could shift the conclusion from metastable to perfectly stable. Second, even if we are in a false vacuum, the calculated timescale for a spontaneous decay is mind-bogglingly long. We're talking numbers with hundreds of zeros after them. time spans that make the 13.8 billion year age of the universe look like the blink of an eye. The probability of it happening in your lifetime, in the lifetime of humanity, even in the lifetime of the Earth, is so infinitesimally small as to be practically zero. You have a far, far, far greater chance of being struck by lightning while winning the lottery. We should not lose sleep over this. This idea, then, is less of a practical warning and more of a profound intellectual tool. It connects the world of the very small, particle physics, with the world of the very large, cosmology. It tells us that the fate of the entire universe might hinge on the precise properties of its tiniest constituents. This forces us to refine our experiments. We build larger colliders and more sensitive detectors, not because we are afraid of vacuum decay, but because the quest to answer this question leads us to a deeper understanding of everything. We want to measure the Higgs boson and top quark masses with ever greater precision to know where we truly stand. Finally, we can find a strange comfort in our own existence. If vacuum decay were easy or likely, it probably would have happened already. The universe has been around for a very long time, and it has seen conditions of much higher energy than anything we experience today, especially in its early moments after the Big Bang. The fact that we are here, in a universe stable enough to form galaxies, stars, and thinking beings, is itself evidence that our vacuum state is, at the very least, extremely long-lived. Our existence is a data point suggesting that our little dip on the hill is a pretty safe place to be. So, we are left with a grand and unsettling thought. We live in a cosmos that may contain the seed of its own undoing. A tiny particle, a flicker of quantum chance, could rewrite reality. You can let that thought fill you with fear, a sense of cosmic fragility that makes everything seem pointless. Or you can choose a different path. You can let it fill you with wonder. See it not as a threat, but as a humbling reminder of the scale and mystery of the universe. This idea forces us to adopt a cosmic perspective. The universe is dynamic. The universe is ever-changing. It operates on timescales that dwarf our human concerns. The same physical laws that create the potential for catastrophe also let stars shine. Planets form, life emerge. The universe is both exquisite creation and potential destruction, woven from the same fabric. Fragility isn't a flaw, it's a feature. It's what makes the cosmos interesting. Thinking about vacuum decay doesn't have to be about the end. It can be the beginning of a deeper appreciation for the present moment. It highlights the incredible serendipity of our existence. In a universe of mind-bending possibilities, here we are. On a stable planet, in a stable solar system, in a seemingly stable patch of space-time, we are here now, able to look up and ponder. That is a miracle worthy of awe. The potential for the end gives meaning to the now. This is why we do science. We push into dark, unknown territories driven by insatiable curiosity. The story of vacuum decay is a testament to how far we've come. We have built theories that can speculate about the end of reality. Do not fear the ghost story of the cosmos. Listen to it. Let it quiet your ego and awaken wonder. The universe is vast, mysterious, and beautiful, and our journey to understand it has only just begun.